Imagine a universe without light, without time, just an immense, dense, motionless, silent darkness. This audiobook invites you to discover the most unknown era of the cosmos, the period before the first photon, an eternal moment where time seemed frozen and matter had not yet shone. What was happening in that opaque universe, and how did the reality we know today emerge from it? The answers could change your perspective on the origin. Forever, in this primordial moment, the universe was nothing more than a dense, hot soup of particles. Imagine a pot of boiling water where each bubble represents a small part of what would eventually become stars, planets, and even us. But how did we arrive at that moment of explosion and expansion known as the Big Bang? The answer is not simple, as it leads us to explore the laws of physics and how they transform under extreme conditions. In the era before the first photon, we find ourselves in a phase of the universe that is practically incomprehensible to our human minds. The laws that govern our everyday world, such as gravity, electromagnetism, and thermodynamics, did not apply in the same way. It was a time when space and time were intertwined in ways we still cannot fully understand. What does this mean for us? It means that the universe was charged with possibilities, waiting for the right conditions to give way to creation. Matter and antimatter, two sides of the same coin, began to emerge from this primordial nothingness. Have you ever wondered why there is more matter than antimatter in the current universe? The answer to this enigma takes us back to the first moments of the Big Bang, where small asymmetries in the production of these two forms of existence laid the groundwork for the reality we know today. Without this difference, the universe would have been a much stranger place, where the annihilation of particles would have reigned instead of life. As we move forward in time, we encounter the theory of cosmic inflation. This phenomenon, which occurred just after the Big Bang, is as if the universe had received a growth spurt. In an incredibly short time, the universe went from being the size of a singularity to expanding at a dizzying speed. Imagine inflating a balloon. At first it is small, but with each breath it expands enormously. What implications does this inflation have for the structure of the universe we see today? The journey through time continues with the era of radiation, a period in which the universe transformed from a hot plasma to a state where particles began to form. This process was like cosmic alchemy, where energy turned into matter. At this point, even light began to play a role, although it was still trapped in a sea of charged particles. The light that would later illuminate the universe was still far from being free. The creation of the first atoms, such as hydrogen and helium, was a fundamental milestone in the history of the cosmos. Imagine each atom as a brick and the universe as a vast construction site. Without these fundamental bricks, we would not have been able to build anything. Neither stars nor galaxies nor life itself. How were these atoms formed, and what impact did they have on the evolution of the universe? However, not everything was light and clarity. There was a period of cosmic darkness where the universe became a silent, empty place, devoid of the light we know today. This emptiness was not just the absence of light, but a state where the universe was calm, waiting for the right moment to take a new step forward. What does darkness really mean in the history of the universe? It is a reminder that even in silence, creation is underway. Primordial nucleosynthesis, the process that gave rise to the lighter elements, took place in the first minutes after the Big Bang. During this short period, the universe underwent fundamental transformations. Extreme conditions allowed atomic nuclei to begin forming, a cosmic dance of particles that laid the foundation for everything that would come after. What secrets does this process hold about the origin of the elements that make up our world? When the era of recombination finally arrived, the universe had changed drastically. Electrons and protons combined to form neutral atoms, allowing light to finally travel freely. This moment was like opening a curtain in a dark theater, letting light flood the stage. How did the universe feel experiencing this new freedom of light? The formation of the first stars was another crucial chapter in our history. These gigantic spheres of gas not only illuminated the sky but also began to shape galaxies. Imagine an artist who, at first, works on a blank canvas. Each star is a stroke that brings the work to life. What role did these first stars play in the evolution of the cosmos and in the creation of new elements? Finally, we arrive at the moment when the first photon was emitted. This instant represents a radical change in the history of the universe, the beginning of light as we know it. It is a milestone that marks the end of opacity and the beginning of visibility. What does this first flash of light really mean for the evolution of the universe and our understanding of it? Exploring this frozen time and the era before the first photon leads us to reflect on our own existence and the vast cosmos that surrounds us. Through questions and discoveries, we delve into the mystery of our origin and the journey that has brought us here. The history of the universe is ultimately a story of transformation and creation, and each of us is a part of this magnificent narrative. What if I told you that billions of years ago, everything we know from stars to planets began with an unimaginable explosion? The Big Bang is the starting point of our cosmic history, an event that not only created the universe but also established the conditions for everything we know to exist. But what exactly is the Big Bang, and why is it so crucial for understanding our reality? Imagine an empty balloon. When you inflate it, it expands and fills with air. The Big Bang was something like that. But instead of air, it was an explosion of energy and matter that gave rise to everything. At the moment of that explosion, the universe was concentrated in an extremely small and dense point. Can you visualize that intensity? In the blink of an eye, that tiny sphere of energy began to expand, giving rise to a constantly growing universe. The conditions during that first moment were unimaginable. The temperature was so high that any form of matter we know could not exist. It was a sea of subatomic particles in total chaos. But what does this mean for us? It means that at that instant, the foundations of everything that would come later began to form. The fundamental forces of nature started to manifest, such as gravity and electromagnetism. Without these forces, none of what we see today could exist. As the universe expanded, it began to cool. Have you noticed how the air feels when you open the door of a freezer? That cold sensation is similar to what happened in the universe. With each passing second, the universe became a little cooler, allowing particles to start coming together. And what was the result of that union? The formation of the first elements, which would be the basis of everything we know, hydrogen and helium. But why are hydrogen and helium important? These elements are like the building blocks of the universe. Without them, there would be no stars, no planets, no life. It's fascinating to think that in those early moments, the story of creation was being written. However, things were not that simple. The creation of matter also brought with it antimatter. Can you imagine two opposing forces in a tug of war? That's how the primitive universe worked. Matter and antimatter were in constant struggle, and their interaction would be essential for the evolution of the cosmos. With the expansion and cooling of the universe, a crucial moment arrived, known as the era of inflation. During this phase, the universe expanded exponentially. Can you imagine a piece of gum stretched to the point that it seems like it will never stop? That's what happened during cosmic inflation. This rapid expansion helped shape the universe, distributing matter in such a way that it could form galaxies, stars, and planets. But before we could see the wonders of the universe, we had to go through the era of radiation. In its early moments, the universe was a hot plasma, a soup of energy and particles. There was only light in the form of radiation, with no solid objects to reflect it. Can you imagine a place full of light, but with nothing to contain it? That was the universe before particles began to organize. Over time, conditions became suitable for the first atoms to form. This process is fundamental because without atoms, we wouldn't have the matter that makes up everything around us. As atoms began to form, the universe went through a period of darkness. But what does that mean? It means that although there was matter in the universe, there was still not enough light to illuminate it. It was like a vast dark ocean, full of potential, but without a lighthouse to guide the way. Primordial nucleosynthesis was another vital step in this narrative. In the first minutes after the Big Bang, the lighter elements, such as hydrogen and helium, formed through nuclear reactions. This process is similar to how a chef mixes ingredients to prepare a recipe. In the case of the universe, these elements would be the essential ingredients for the formation of stars and galaxies. As time passed, the era of recombination arrived, a moment when protons and electrons finally combined to form neutral atoms. This was a crucial change as it allowed light to begin traveling through the universe. Before this, the universe was opaque, filled with particles that scattered light. It was like trying to see through a dense cloud. But once the atoms formed, the universe became more transparent, allowing light to begin its journey. Have you ever seen how the first lights of dawn illuminate the sky? That's how it was when the first stars formed. These stars, composed mainly of hydrogen and helium, began to shine in the darkness of the cosmos. Each one was like a spark in a vast ocean of darkness, marking the beginning of a new era in the history of the universe. Finally, that first photon, that tiny unit of light that emerged from the primitive chaos, had a monumental impact. This photon not only illuminated the universe, but also symbolizes the moment when the universe began to be a place where light could travel freely. It was the first step toward the creation of everything we know today. From that moment on, light began to fill the cosmos, giving life to galaxies and the structure we can observe today. In summary, the Big Bang was not just an isolated event, it was the beginning of an incredible story that has unfolded over billions of years. From the creation of the first elements to the formation of the first stars, each step was essential in shaping the universe we know. By understanding this process, we not only grasp the past, but also glimpse the future of the cosmos and our place within it. The Planck era is like the first chapter of a book that tells an incredible story, a period in which everything we know about the laws of physics is called into question. In those first moments of the universe, less than a second after the Big Bang, the conditions were so extreme that gravity, time, and space, as we understand them today, did not exist. But how can one imagine a moment when the rules of the universe were completely different? To understand this stage, let's think of a calm ocean. On the surface, everything seems tranquil, but powerful and turbulent currents hide in the depths. That's how the universe was in its infancy, a dense and hot soup of subatomic particles in a state of chaos. In this era, everything was energy. Matter, as we know it, had not yet had the chance to emerge. So what was happening in this sea of energy? String theory, although still in development, suggests that at this primordial moment, the fundamental forces of nature, such as gravity and electromagnetism, were united. Imagine a gigantic musical chord where all the notes sound in unison, but as the universe expanded and cooled, this harmony broke apart, giving rise to the different forces we know today. How is it possible that such a brief moment can have such a lasting impact on the structure of the cosmos? The Planck era extends to just 10 raised to the power of -43 seconds after the Big Bang. Can you imagine a time so small that it is hard to conceive. In this brief span, energy transformed into particles and antiparticles, creating a fleeting balance. But why is this delicate balance so important? What would have happened if one of those particles had prevailed over the other? Matter and antimatter, two sides of the same coin, emerged from this energy. However, for reasons we still do not fully understand, it seems there was more matter than antimatter. Did the universe have a plan from the beginning? This imbalance is what allowed matter, our tangible world, to exist. If the amount of matter and antimatter had been equal, we would have nothing around us, no planets, no stars, not even atoms. As the universe continued to expand, the temperature began to drop. This era of extreme heat was the perfect setting for particles to start interacting and forming bonds. But how does a primordial explosion transform into the cosmos we know today? The laws of physics, as we understand them, do not apply in this context. It is a territory where human intuition meets the unknown. At this stage, gravity also began to make its appearance. Although it was still extremely weak, it started to influence how particles group together. Could it be that gravity was the first force to set the pace for the evolution of the universe? The Planck era raises more questions than answers, opening the door to a fascinating mystery about the origin of our cosmos. But not everything was chaos. As the universe continued its expansion, the foundations for what would come next began to be established. The first interactions between particles led to the formation of the first elements. This process is like the beginning of a recipe where the ingredients start to combine to create something new. However, the recipe was not yet ready. The universe needed more time to cook. The Planck era is a reminder that the universe is a place full of surprises. It invites us to reflect on what it really means to exist. Is it possible that in that primordial instant, the universe was preparing for the complexity that would come? Could it be that everything we are and everything we know is rooted in that moment of pure energy? Looking back at the history of the universe, it is astonishing to think that everything began in this era. The questions that arise are as numerous as the stars that would eventually fill the sky. What mysteries still await us in the folds of time and space? The Planck era is just the beginning, a window into a cosmos full of possibilities and wonders. So as we reflect on this crucial moment, let us remember that every discovery we make about the universe brings us closer to understanding our own existence. The Planck era teaches us that although the past is an enigma, every answer we find is a step toward a future filled with light and knowledge. Are we ready to keep exploring? In the early moments of the universe, just after the Big Bang, a fascinating phenomenon occurred, the creation of matter and antimatter. But what does this really mean? To understand it, we must delve into a world where the rules of physics as we know them do not fully apply. A world in which energy and matter are engaged in a cosmic dance, creating and destroying at a dizzying pace. Let's start by defining what antimatter is. Imagine that every particle of matter has its counterpart in the world of antimatter. For example, the electron, which is a particle with a negative charge, has an equivalent called the positron, which has a positive charge. In this sense, antimatter is like a reflection in a mirror. It is identical but opposite. But how do these two entities form in such a young and chaotic universe? At the moment of the Big Bang, an immense amount of energy was released. This energy could transform into particles of matter and antimatter. According to the principles of quantum physics, energy can be converted into particles. Thus, in an incredibly brief instant, pairs of particles and antiparticles began to be created. But why didn't they equalize in number and annihilate each other, leaving only energy? This is where the story becomes intriguing. As the universe expanded and cooled, conditions began to change. In this new cosmic landscape, it is believed that there was a slight imbalance between matter and antimatter. This small excess of matter, which might seem insignificant, turned out to be crucial. Can you imagine a universe where matter and antimatter were perfectly balanced? In that case, we wouldn't be here to discuss the creation of the cosmos. The process of forming matter and antimatter is like a game of chance in which fate decided that a little more matter would win. This imbalance allowed matter to survive, while antimatter quickly annihilated itself in explosive encounters with its counterpart. In the blink of an eye, the first particles of matter settled, laying the groundwork for everything that would come afterward. But what role did these particles play in the evolution of the universe? The first particles of matter, such as quarks, combined to form protons and neutrons. These, in turn, grouped together to create atomic nuclei in a process that would be fundamental for the creation of the elements that make up our universe. Without this first step, atoms would not have existed, and matter as we know it would never have taken shape. The creation of matter and antimatter also leads us to reflect on the very nature of the universe. Why is there this difference between matter and antimatter? Some scientists believe there may be a type of broken symmetry in the laws of physics that favors matter over antimatter. This is a fascinating mystery that continues to intrigue physicists around the world. As the universe continued to expand and cool, particles began to combine in increasingly complex ways. Protons and neutrons joined together, forming atomic nuclei of hydrogen and helium. Undoubtedly, these initial interactions were fundamental for the development of later stars and galaxies. Have you ever imagined how the elements that make up your body were created in those primordial moments? The delicate balance between matter and antimatter paved the way for the structure of the universe. If matter had not surpassed antimatter, there would be no stars, planets, or even us today. The story of matter is, in a way, a story of survival, a tale of how what seemed like a simple game of particles became the foundation of all existence. The study of this process is not only important for understanding our origins, but also raises profound philosophical questions. If matter is predominantly what exists, what does this mean for our understanding of the universe? What kind of cosmos would we have had if antimatter had the advantage? Moreover, the creation of matter and antimatter is not just a phenomenon of the past. Scientists continue to investigate how these particles behave in the present. In particle accelerators, they attempt to recreate conditions similar to those of the Big Bang, seeking answers to questions that remain unanswered. The story of matter and antimatter is a reminder of the beauty and complexity of the universe. It shows us that, at its essence, everything is interconnected. Every star in the sky, every leaf on a tree, every breath we take comes from those first moments of creation. Thus, the story of matter is also the story of our existence. In summary, the creation of matter and antimatter in the early moments of the universe was a fundamental event that laid the groundwork for everything we know. Through a delicate balance, matter emerged victorious, allowing life and the cosmos to develop. This fascinating tale invites us to explore not only our origins, but also our place in the vast stage of the universe. If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this Star Odyssey. Cosmic inflation, a fascinating phenomenon, manifests as a crucial moment in the history of the universe. While it is difficult to imagine, let's consider the magnitude of what occurred. In a fraction of a second, the universe expanded exponentially, almost as if a bubble suddenly inflated. But in this case, the bubble was the cosmos itself. What caused this dizzying expansion? The answer lies in the extreme conditions that prevailed at that time, where matter and energy were in an almost primitive state. As the universe emerged from the Big Bang, it was filled with incredibly dense and hot energy. But what does that really mean? Imagine you are in a confined space. where everything is compressed to a tiny size and suddenly you feel a pressure pushing you outward. That's what happened to the universe. Cosmic inflation tells us how that initial energy, which was once concentrated, dispersed, creating the space we know today. You may wonder, why is cosmic inflation so important? The answer lies in how this initial explosion helped establish the foundations for what would come next. Without this rapid expansion, the universe might have remained in a chaotic state where the structures we see today, galaxies, stars, and planets, would not have had the opportunity to form. Just as in a kitchen where ingredients must be in the right order to prepare a delicious dish, inflation organized the universe in a sequence that allowed it to evolve. But where does energy fit into all this? During inflation, energy transformed, and that transformation was key. From this primordial energy arose the small fluctuations that would give rise to matter. These tiny variations in the density of the universe are similar to the small bubbles that form in a liquid when heated. Each bubble represents a point where matter could begin to condense and form the structures that would eventually lead to galaxies. Now let's consider an intriguing aspect: the speed of expansion. Cosmic inflation was not just fast, it was absurdly rapid. Imagine you are on a train traveling at the speed of light. In comparison, the expansion of the universe at that moment was as if the train was standing still. This speed allowed regions of the universe to separate from each other before they could make contact, creating a vast homogeneous space that would later be filled with galaxies. However, it wasn't all that simple. As the universe expanded, it began to cool. What happens when a balloon is inflated? It stretches and eventually cools down. This cooling was fundamental for energy to convert into particles. The extreme conditions that once prevailed began to give way to a more manageable universe where the formation of matter would be possible. Cosmic inflation also offers us another intriguing perspective. Imagine the universe is filled with a kind of cosmic snow, a mix of particles and energy that, as it expands, spreads throughout space. This snow began to settle, forming the backdrop for the creation of everything we know. Without that phase of inflation, we might not have a universe as diverse as the one we observe today. But how can we know that cosmic inflation really occurred? Scientists have turned to the observation of gravitational waves and the cosmic microwave background radiation, which are echoes of that initial explosion. Just as an echo helps us understand the shape of a cave, these waves give us clues about the structure of the universe in its early moments. This connection allows us to reconstruct the history of the cosmos, showing how each stage intertwines with the next. As we reflect on cosmic inflation, it is essential to remember that this event was not just a physical phenomenon, it also raises philosophical questions. What does it mean for us, inhabitants of this vast universe, to understand that everything we know began with such a dramatic expansion? The history of the universe is not just a tale of matter and energy, but a story of transformation and potential. Every aspect of cosmic inflation invites us to think beyond what we know. While science has made great strides, there will always be a mystery that drives us to keep exploring. What else could the universe reveal about its past, and how might this affect our future? Curiosity leads us to seek answers, and in this journey, each discovery becomes a spark that illuminates our understanding. So, as we contemplate cosmic inflation, let us remember that we are observing an evolving story where each chapter is crucial. From the primordial explosion to the formation of galaxies, each event brings us closer to unraveling the secrets of the cosmos. Cosmic inflation is not just a phase in the history of the universe, it is the beginning of everything, a testament to the greatness of what we are and what we can become. How does a hot, dense universe transform into a space where particles begin to exist? In this crucial phase known as the era of radiation, the universe undergoes a fascinating metamorphosis. Imagine a vast ocean of boiling energy, where conditions are so extreme that atoms cannot form. During this period, the universe is filled with particles and radiation, but there is still no matter as we know it. The era of radiation begins a few minutes after the Big Bang. During this time, the universe is a soup of subatomic particles, where electrons, positrons, and photons interact frantically. What does this mean for the cosmos? The answer is that this energetic chaos is fundamental to the birth of matter. As the universe expands, it cools, allowing particles to start forming the first atomic nuclei. Have you ever wondered how atoms are formed? At this point, the temperature of the universe is so high that electrons cannot join protons and neutrons to form stable atoms. However, as the universe continues to expand and cool, the perfect conditions are created for this to happen. When the temperature drops to about 1 billion degrees, electrons can finally join the nuclei, forming hydrogen and helium atoms, the building blocks of the universe. During the era of radiation, light and matter are in a constant dance. Photons, which are particles of light, interact with electrons and nuclei in a process called scattering. This process creates an environment where radiation is omnipresent, meaning that if you could see this primitive universe, you would find yourself in a bright sea of light and energy. But what happens when the universe cools even further? As the temperature drops, the energy of the photons decreases. This is crucial because the photons, which were previously like a bouncing ball of energy everywhere, begin to lose their ability to interact with particles. Upon reaching a critical point, photons can finally travel freely through space. This marks the beginning of a monumental transformation, as light can move without being scattered. Why is this change important? Imagine a concert in a packed stadium. At first, the sound gets lost in the noise of the crowd, but when the audience falls silent, you can hear every note perfectly. This is how light manages to travel through the universe. This release of photons marks the beginning of a new chapter in cosmic history, the era of recombination. In this phase, the universe also becomes a clearer place. Before, photons were trapped in a kind of fog of charged particles. But as electrons combine with protons to form neutral atoms, the universe becomes more transparent. This moment is crucial because it sets the stage for the formation of the first structures in the universe. The era of radiation is not only a period of physical transformation, but also raises fascinating questions. How did this period influence the formation of galaxies? The answer lies in the way matter began to clump together. As hydrogen and helium atoms formed, gravity began to play a fundamental role, attracting these particles and creating the first structures that would eventually become stars and galaxies. The end of the era of radiation is not just a physical change event, but it also triggers a series of reactions that directly impact the evolution of the universe. By releasing the photons, the door opens to the light of the first stars, which will shine in the darkness of the cosmos. But how do these stars form from a universe that, in its early moments, was just energy and particles? This period lays the groundwork for what is to come. The light generated by the first stars will illuminate the universe, marking the end of darkness and the beginning of a new era. However, the era of radiation is not just a moment in time. It is a reminder of how, from extreme conditions, a cosmic order can emerge, giving rise to the beauty we observe today in the sky. We can think of the universe as a great blank canvas. During the era of radiation, colors and shapes begin to appear, albeit still in a diffuse manner. This period establishes the necessary conditions for the first stars and galaxies to be drawn, and eventually everything we know and appreciate in the cosmos. So the question that remains is, What else was forged in this primitive cauldron that would shape our current universe? Each of these steps in the era of radiation is a brick in the construction of the cosmos. The light we see today is the echo of those first vibrant moments, reminding us that even in chaos, there is an order that can emerge. How will we understand what happened after this period? The answer will lead us to explore the fascinating stages that follow. But that is a story for another time. In the dawn of the universe, when everything was chaos and extreme temperatures, something marvelous was born: matter. But how did it form exactly? The answer to this question takes us to the first moments after the Big Bang, where everything began to take shape. At that instant, what we know today as matter did not exist. Instead, the universe was in a state of pure energy, a hot soup of fundamental particles and radiation. Matter, in its simplest form, is composed of atoms, but before these could exist, the universe had to cool down enough for particles to come together. Can you imagine a party where no one dares to dance because the music is too loud? That's how the universe was, with such intense energy that particles couldn't get close to one another. But as the universe expanded and cooled, conditions began to change. The music started to lower in volume, and particles began to dance together. In this hostile environment, the first major challenge was the creation of quarks and gluons, the fundamental pieces that make up protons and neutrons. How are these building blocks formed? Quarks joined in groups of 3 to form protons and neutrons, while gluons acted like the glue that held them together. It's like having a group of friends who, upon finding a warm spot, decide to form a circle and not let go. However, the story doesn't end there. For every proton that formed, its counterpart, the antiproton, also emerged. What does this mean? For every particle of matter, there was a particle of antimatter. It was as if the universe was in a constant dance between creation and destruction. But why is this duality so important? The existence of matter and antimatter is crucial for understanding how our cosmos evolved. At that moment, matter and antimatter were in a constant struggle, like two teams competing in a soccer match. So what happened to all that antimatter? As the universe continued to expand and cool, a fascinating phenomenon occurred. During this phase, more matter began to form compared to antimatter. However, why did matter win? Although we still don't have a definitive answer, this asymmetry is one of the great mysteries of physics. Imagine that in that soccer match, one team managed to score more goals than the other, and thus our universe filled with matter was born. The conditions in the universe were so extreme that not only were protons and neutrons forming, but also electrons. These were the little spectators that, after joining with protons, would give rise to the first atoms. But how does this happen? Electrons joined the nuclei of hydrogen and helium in a process that required the universe to cool down even further. It's a bit like when hot water starts to form steam, and as it cools, it turns into droplets of water. The creation of these first atoms marked a crucial milestone in the history of the universe. Without those hydrogen and helium atoms, we wouldn't have the stars or planets we know today. Think of it like building a house. First, you need the foundation before you can raise the walls. Primordial matter became the base upon which everything we know would be built. Over time, the universe began to fill with these atoms, creating a kind of soup of matter ready to be shaped. But even though matter was already present, the universe was still a dark place, devoid of light. What does this mean for us? Without light, it would be impossible to see the splendor that was to come. However, that darkness wouldn't last forever. The formation of the first atoms was just the beginning. As the universe continued its expansion, these atoms began to cluster together, forming gas clouds that would become the first stars. But before reaching that bright stage, the universe needed a bit more time and space to develop. Like an artist needing a blank canvas before starting to paint, the universe was preparing to create something extraordinary. It's fascinating to think about how all of this connects, from a state of pure energy to the creation of the first atoms. Each step was essential in shaping our cosmos. Matter and antimatter, quarks and electrons, everything was interconnected in a cosmic dance that led to the creation of our universe. Undoubtedly, the story of matter is a story of transformation, where what was once chaos became order and beauty. Thus, matter began its journey, and with it, the possibility of life. Every atom that makes up our body has its roots in those first moments of the universe. Reflecting on this invites us to look up at the sky and ask ourselves, what other wonders are hidden in the vastness of the cosmos? The story of matter is not only the story of our universe, but also ours. In the vast and mysterious universe, there is a fascinating moment when everything was shrouded in darkness, a period that scientists have termed the cosmic darkness. But what does this darkness really mean? And what implications does it have for our understanding of the cosmos? The answer to these questions takes us on a journey through time to a universe where light had yet to make its grand entrance. In the beginning, everything was a fiery chaos. The universe in its early moments was a sea of subatomic particles, a place where the temperature was so high that light could not travel. In this era, particles were constantly colliding, creating a state in which nothing could be seen. Imagine an ocean of pure energy, where each wave is an explosion of activity, but where light, like an elusive fish, cannot find its way. This era of opacity, where light was trapped in a sea of particles, lasted for hundreds of thousands of years. As the universe expanded and cooled, conditions began to change. But why is it so important to understand this period of darkness? The answer lies in what happened next. As the universe cooled, particles began to come together, forming simple atoms like hydrogen and helium. This process was essential as it laid the groundwork for the formation of stars and galaxies. However, before that could happen, the universe had to go through a phase of darkness where light simply could not escape. In this stage, the universe was a quiet and silent place without the glow of the stars we know today. But can there be beauty in darkness? Definitely. The cosmic darkness represented a time of preparation when the universe was aligning the pieces of the cosmic puzzle. It was a period of waiting, a moment when everything was calm before the explosion of light and activity that would come. One might wonder, how did the universe feel during that time? Although we cannot feel it as humans, we can imagine it was a state of infinite potential. Everything we know today, from twinkling stars to vast galaxies, was about to be born. But first, the universe had to learn to be what it is, and that involved going through darkness. The end of this era of opacity was marked by a crucial event, the era of recombination. During this period, electrons and protons combined to form neutral atoms, allowing light to finally travel freely. This moment was like opening a window in a dark room, letting in sunlight for the first time. But before reaching that light, the universe had to go through its phase of darkness, a time that, although empty of light, was full of possibilities. Now, let's think about the importance of darkness in our daily lives. In everyday life, darkness can seem uncomfortable or even frightening, but it is also a time for rest and reflection. Similarly, the cosmic darkness was a time of rest for the universe, a necessary period for light to arrive and bring life to what we know. Without this phase of calm, the universe might not have been able to organize itself to form the complexity we see today. The cosmic darkness reminds us that we cannot always see the way forward. Sometimes, phases of uncertainty are essential for growth and evolution. This period in the history of the universe teaches us that light is beautiful, but darkness also has its own intrinsic value. Every star that shines in the sky today is a reminder that, even when everything seems dark, light is always about to emerge. As we reflect on the cosmic darkness, another intriguing question arises. How long did it really last? Although it may seem like a long period, in cosmic terms, it was just a fraction of time. However, its impact is monumental. This period has influenced the way we perceive the universe and our place in it. Every galaxy we see today is the result of a universe that, at one point, had to face darkness in order to shine. Therefore, as we look up at the night sky, let us remember that behind every star lies a past full of mystery and darkness. The cosmic darkness was not simply a void, but a canvas on which the history of the universe was painted. As we continue our journey through the cosmos, it is essential to understand that light cannot exist without darkness. Thus, the cosmic darkness becomes a vital chapter in the narrative of our universe, a reminder that hope and potential are always present, even in the darkest moments. The next time you gaze at the starry sky, remember that you are not only seeing light, but also the legacy of an era that, though dark, was crucial for the creation of everything we know. The cosmic darkness, with its mysterious beauty, invites us to contemplate the vast universe, reminding us that every star has a story to tell, and that every story begins in the silence of darkness. In the early moments after the Big Bang, the universe was an extremely chaotic and hot place, where conditions were so extreme that matter as we know it could not exist. Have you ever wondered how the first elements formed amid so much chaos? The answer lies in a fascinating phenomenon known as primordial nucleosynthesis, a process that took place in the first minutes of the universe's existence when everything was pure energy. Did you know that? In those initial moments, the universe was primarily composed of subatomic particles like quarks and gluons, but there were no atoms. These quarks combined to form protons and neutrons, the building blocks of matter. But what happened next? As the universe expanded and cooled, these protons and neutrons began to join together in a process that would give rise to the first atomic nuclei. Imagine a large factory of elements where, as the temperature dropped, workers began assembling pieces to form products. In this case, those products were hydrogen and helium nuclei. Primordial nucleosynthesis allowed about 75% of the universe to become hydrogen, the simplest and most abundant element, while the remaining 25% transformed into helium. But why are these elements so important? Hydrogen and helium are not just the fundamental bricks of the universe. They are also the raw materials of stars. When the first stars later formed, these elements became the fuel that would power nuclear fusion, the process that gives life to stars and in turn produces heavier elements. Isn't it amazing to think that the atoms that make up our own bodies were created in the hearts of stars that lived and died billions of years ago? However, primordial nucleosynthesis was not a perfect process. Although large amounts of hydrogen and helium were formed, other heavier elements, such as carbon and oxygen, were not forged at this time. Can you imagine why? The answer lies in the temperature and pressure required to create heavier elements, which simply were not present in those early minutes of the universe. The creation of the first nuclei was not only crucial for the formation of stars, but it also established the foundation for the structure of the universe. Without those first nuclei, there would not have been enough matter to form galaxies, planets, and eventually life as we know it. But what happened to antimatter during this process? For every particle of matter that formed, there should have been a corresponding particle of antimatter. However, in the current universe, it seems that there is much more matter than antimatter. Where did all that antimatter go? Scientists are still investigating this mystery. The asymmetry between matter and antimatter is one of the great enigmas of the cosmos. What happened in those early moments that allowed for an excess of matter to form? This is a puzzle that continues to challenge physicists and cosmologists, and every clue they uncover brings us a little closer to understanding the nature of the universe. As the first nuclei formed and the universe continued to expand and cool, what do you think happened to the energy that still remained in the medium? That energy dispersed, but it also allowed conditions to become more favorable for the formation of atoms. Over time, primordial nucleosynthesis laid the groundwork for the next great chapter, the formation of neutral atoms. With the formation of the first nuclei, the universe was on its way to becoming a place where light could exist. In this sense, primordial nucleosynthesis was not just a chemical event. It was a milestone in the history of the cosmos, a moment that allowed the universe to begin to take shape. Thus, the path toward the creation of stars and galaxies was charted, and the story of the universe began to unfold. However, primordial nucleosynthesis was not the only process that shaped the composition of the universe. As stars began to form and fuse hydrogen into helium, they also began to create heavier elements within themselves. This leads us to the question, what role did these stars play in the creation of the elements that make up our world? The answer to this question is fundamental to understanding the history of the universe and our own existence. Without the supernova explosions that scattered those elements across the cosmos, there would not have been enough material to form new stellar systems, including our own solar system. Thus, primordial nucleosynthesis was just the first step in a much broader process that continued for billions of years. In summary, primordial nucleosynthesis was not only an event that allowed for the creation of the first atomic nuclei, but it was also a crucial moment in the history of the universe that laid the foundation for the formation of stars, galaxies, and eventually, life. As we delve into the vast cosmos, it is important to remember that every atom that makes us up has a story that began in those chaotic and energetic moments of primordial nucleosynthesis. The era of recombination is a fascinating stage in the history of the universe, a crucial moment that marked the end of cosmic opacity. But what does recombination really mean, and how did it influence the formation of the cosmos as we know it today? To understand this, it's important to go back a bit in time, to when the universe was an extremely hot and dense place, where light could not travel freely. In those early moments, the universe was filled with subatomic particles, electrons, protons, and a variety of other particles. However, the temperature was so high that these particles could not come together. Imagine a huge dance where all the participants are so agitated and excited that they cannot find each other or form pairs. That was the universe in its infancy. The particles were constantly colliding with each other, keeping the cosmos in a state of chaos. As the universe expanded, it also cooled. This cooling was a gradual but crucial process. At the moment when the temperature reached a critical point, something extraordinary happened. The electrons, which had been free and scattered, began to join with protons to form hydrogen atoms. This process, known as recombination, was like dancers finally finding their partners and starting to form groups. Suddenly, the universe became more ordered. Why is this moment so important? The answer lies in light. Before recombination, light was trapped in that sea of charged particles. It was like trying to see through a fogged-up window. Nothing could penetrate the haze of energy and matter. But when electrons and protons came together to form atoms, the universe became transparent. Light could finally travel freely. Can you imagine what that meant? It was as if the windows of a dark basement were opened, allowing sunlight to flood the space. This new state of the universe allowed light to propagate, and with it, the structure we know today began to form. The light emitted at that moment has become what we now call the cosmic microwave background radiation, an echo of that instant. But how can we be sure that this really happened? The answer lies in science. Astronomers have detected this radiation and studied its signature to understand what happened during those crucial moments. As the universe continued to expand and cool, other elements began to form as well. Although hydrogen and helium were the first, recombination laid the groundwork for the creation of more complex elements in later generations of stars. After all, without this first step, we would not have the elements necessary to form planets, life, and even ourselves. The era of recombination is also significant because it allowed the first cosmic structures to begin forming. Gravity began to play a fundamental role. Hydrogen atoms grouped together and formed gas clouds that would eventually collapse to give rise to the first stars. This was the beginning of a long history of star formation that would lead to galaxies, galaxy clusters, and ultimately the vast universe we see today. Imagine a huge blank canvas. Recombination was the first stroke of color applied to that canvas. As more and more stars began to shine, the universe filled with light and color, becoming a vibrant and lively place. But it is also important to remember that despite this new clarity, the universe still faced challenges. Dark matter and dark energy would play key roles in the evolution of the cosmos, but that is a story for another time. The era of recombination reminds us that beginnings are often chaotic and disorderly, but they are also the starting point for something extraordinary. Without that crucial moment when electrons and protons came together to form atoms, the universe would not be the rich and diverse place we know today. It is a testament to the power of physics and nature and how sometimes the smallest moments can lead to colossal changes. The legacy of recombination is, in many ways, a symbol of hope. It teaches us that even in the most difficult circumstances, order can arise from chaos. As the universe continued its journey, possibilities expanded, giving rise to life, stars, planets, and ultimately humanity itself. This story of transformation is an invitation to reflect on our own place in the cosmos and the wonder of existence. So the next time you look at the starry sky, remember that every star you see, every galaxy that shines in the darkness, has its roots in that crucial moment of recombination, when the universe decided to stop being an opaque place and began to shine with light and life. The era of recombination is more than an event in the history of the universe. It is a reminder that what is visible and understandable today had its origin in mystery and wonder. The first stars of the universe are like beacons in a dark and unknown ocean. At a time when the cosmos was shrouded in darkness, these stars began to shine, marking the beginning of a new era. But how did these lights emerge from the shadows? The answer to this question takes us on a fascinating journey through the history of the universe. Imagine a place where matter had not yet organized into recognizable forms. Just after the Big Bang, the universe was a dense and hot soup of subatomic particles. Amidst that turmoil, gravity began to work its magic. The small fluctuations in the density of matter were the first step toward the formation of stars. You can think of this as inflating a balloon. As air accumulates in certain areas, the balloon starts to deform, creating bulges. In this way, gravity began to pull matter toward these denser areas, as if creating small bubbles in that vast ocean of particles. But what happened after the matter clumped together? As these bubbles grew, the pressure and temperature inside them increased. It's similar to what happens when you boil water in a pot. As heat builds up, the water starts to boil. In the case of the universe, this boiling of particles eventually led to a critical stage, nuclear fusion. This is what turned those gas bubbles into the first stars. The first stars were not like the ones we see in the sky today. They were enormous, bright, and interestingly composed almost entirely of hydrogen and helium, the simplest elements. Imagine these stars as gigantic nuclear furnaces where hydrogen is converted into helium through a fusion reaction. This process not only generates light and heat, but also releases a tremendous amount of energy. With each passing second, these stars shone brighter and brighter, illuminating the universe that had previously been in complete darkness. The life of these primordial stars was not eternal. Over time, they exhausted their fuel and began to die, but their death was not in vain. By exploding in powerful supernovae, they released a vast amount of heavier elements into space. It's as if at the end of their lives, these stars were sowing the cosmos with the ingredients necessary to form new worlds. Without those explosions, the universe would be a very different place, lacking the diversity of elements that allow for the formation of planets and life. What impact did these first stars have on the evolution of the universe? Their light began to ionize the surrounding hydrogen, creating a process that marked the end of the era of darkness. This phenomenon became known as reionization, and it was a crucial moment in cosmic history. The light from these stars not only illuminated the universe, but also began to shape the structure of what we now know as galaxies. With the formation of the first stars, the universe transitioned from a uniform and dark place to one filled with light and activity. Stars began to group together, forming the first galaxies. Each galaxy is like an island in the vast ocean of space, where stars live, die, and give birth to new stellar systems. Without the first stars, the diversity of the universe we know today simply would not exist. It is astonishing to think that those ancient gas giants, which lived and died billions of years ago, laid the foundations for everything that exists in the cosmos. From the planets orbiting new stars to the molecules that form life itself, everything has its origin in those initial moments. Without the first stars, we would not be here to contemplate the universe. In the context of our own existence, the story of the first stars offers a unique perspective on our place in the cosmos. Every atom in our bodies was forged in the heart of a star. So, when you look up at the starry sky, remember that you are not just observing distant lights, but the remnants of a cosmic past that connects us all. The story of the first stars is a reminder that, despite the vastness of the universe, we are intimately linked to its history. Every star that shone in the darkness has contributed to the cosmic symphony that surrounds us. From the atoms that make up our blood to the galaxies that populate the sky, everything is interconnected. With each discovery about the first stars, we also learn more about our own history. Humanity's curiosity to understand the cosmos is not just an intellectual exercise, it is a quest for our identity in the vast universe. By exploring the origin of stars, we are also asking about the origin of ourselves. So, the next time you look up on a clear night, think about the incredible story behind each point of light. The first stars not only illuminated the universe, but also ignited the spark of curiosity within us. The exploration of the cosmos is ultimately an exploration of who we are and where we come from. The first photon, a magical moment that marked the birth of light in our universe. But what does it really mean that the first photon was emitted? To understand this crucial moment, it is helpful to think of the universe as a vast dark ocean before the first lights were turned on. This ocean was full of potential but completely calm, waiting for that spark that would transform it forever. When we talk about the first photon, we refer to the first particle of light that was released in the universe. But why is this event so important? Imagine you are in a completely dark room. You can't see anything, and everything seems to be in absolute silence. Now, if you light a small candle, that light expands and reveals everything around you. In the same way, the first photon illuminated the universe, allowing its story to begin to be visible. Before that moment, the universe was a very different place. Temperatures were extremely high, and matter was so hot and dense that photons could not move freely. It was as if they were trapped in a massive traffic jam, unable to advance. But at the moment the first photon was emitted, everything changed. Matter began to cool, and the first atoms formed, ushering in a new era of expansion and growth. What happens when a photon is released? This small packet of energy travels at the speed of light, which is the maximum speed in the universe. Think of a soccer ball being kicked in an empty field, just like the ball that moves away. The photon disperses, carrying with it the history of the universe. This first photon not only illuminated, but also carried information. Each photon carries within it the imprint of the environment in which it was created, meaning it can tell the story of the events that surrounded it. The emission of the first photon was also the beginning of a series of chain reactions. With each photon that was released, more were created. It's like when you light a spark in a wood stove, you start to see how the fire comes alive and warms the surroundings. As the universe expanded, light spread everywhere, and the cosmos began to become the dynamic place we know today. This moment was not only crucial for light, but also for the formation of structures in the universe. With the first photon, conditions began to form for matter to clump together, creating the first stars and galaxies. Without that first spark, it is hard to imagine how the universe would have evolved. It would be like trying to build a house without bricks. It simply wouldn't work. Light also plays a fundamental role in how we perceive the world. In a more philosophical sense, the first photon can be seen as a symbol of knowledge and discovery. Since that first flash, humanity has been on a constant quest to understand the universe. Every time we look at the starry sky at night, we are observing light that has traveled billions of years to reach our eyes. Some might wonder what happened to the photons that couldn't escape. Many of them found themselves trapped in a sea of particles, unable to break free. However, that opacity was essential in the early moments of the universe. The interaction between light and matter was what eventually allowed the universe to become transparent, paving the way for the era of radiation and the formation of atoms. The importance of the first photon also extends to our understanding of the laws of physics. This event pushes us to question and explore how forces work in the universe. Every time a scientist observes the light from a distant star, they are looking back in time, trying to unravel the secrets that the universe has to offer. Light has become the vehicle that allows us to investigate what was once invisible. As we explore the history of the universe, the first photon becomes a symbol of our longing to discover. It reminds us that although the universe may have begun in darkness, there is always the possibility of light. What will be the next spark that ignites our curiosity? The search for knowledge never ends, and each discovery brings us closer to understanding our place in the cosmos. This first photon teaches us that even the smallest of events can have a monumental impact. Everything we see and experience around us has its origin in that moment. Thus, the first photon not only illuminated the universe, but also ignited the flame of human curiosity, leading us to ask questions about our origin and our future. In conclusion, the first photon is not just a scientific event. It is the beginning of our story as conscious beings seeking to understand our existence. From that first flash of light to the vast universes we observe today, each photon tells a story, and although the universe is vast and often perplexing, there will always be light in the darkness guiding us toward the unknown. The light of the first galaxies is a fascinating topic that leads us to reflect on the origins of the universe and how darkness was slowly replaced by the brightness of stars. Before these galaxies began to illuminate the cosmos, the universe went through a period of opacity, a time when light could not travel freely. But what did that opacity really mean, and how did it transform into light? Visualize a vast dark ocean where the waves stir, but the surface is covered by a thick fog. In this ocean, the creatures that inhabit it live in total darkness, unaware that sunlight exists. That was the universe before the first galaxies began to form. During this time, the universe was filled with charged particles that absorbed and scattered light, creating an environment where visibility was almost non-existent. Light, in this context, was like a traveler trying to cross a dense forest. Every time it tried to move forward, it encountered branches and leaves that blocked its way. However, as the universe began to cool and expand, conditions changed. Charged particles started to combine and form atoms, in a process similar to how the branches of a tree part to let sunlight through. This crucial moment allowed light to begin to flow. But how did this transformation occur? The key lies in the recombination of electrons and protons that join to form neutral atoms. Imagine that each electron is a playful child who finally finds a companion to play with. This union not only allowed for the creation of atoms, but also opened the door to light. Once the atoms were formed, the universe became more transparent. Light began to travel freely, like a river flowing without obstacles. But what happened to that light? It was the light of the first stars, which began to shine in the darkness. However, these stars were not the only ones playing a role in this story. Galaxies also began to form, grouping stars and gas into massive structures that we can still observe today. When the first galaxies began to emit their light, the universe was in a state of transformation. Each flash of light was like a spark of hope in a vast ocean of darkness. But why is this light so important to us? The light of the first galaxies provides valuable information about the history of the universe. Through it, astronomers can understand how the structures we see today were formed and how the cosmos has evolved over billions of years. The light from these galaxies not only illuminates the universe, but also acts as a beacon for scientists. By studying this light, they can trace the evolution of the first stars and consequently the formation of the elements that make up everything we know, from planets to living beings. But what happens when light encounters matter? This encounter generates complex interactions that have shaped the universe as we know it. The light of the first galaxies also helps answer intriguing questions about the nature of the universe. For example, how fast is it expanding? What role does dark matter play in the formation of these galaxies? Through the observation of light, scientists are working to unravel these mysteries as if they were solving a cosmic puzzle. Every time we observe a distant galaxy, we are looking back in time. The light we see today may have left that galaxy billions of years ago. This allows us to have a window into the past, an opportunity to understand how it all began. But what if there is more than what we see? The light of the first galaxies may be just a part of a larger story, a cosmic narrative that continues to unfold. Light not only illuminates the cosmos, it is also a reminder of how fleeting the universe can be. Every star that shines in the sky has its own story, and the light we see today may be on its way to disappearing tomorrow. This leads us to reflect on our own place in the universe and how we interact with it. At the end of this journey through darkness and light, one persistent question remains: what does the future hold for us? The first galaxies have illuminated our path, but the universe continues to expand and change. As we continue to explore, we are likely to discover much more than we ever imagined. The light of the first galaxies is not just a physical phenomenon, it is a symbol of human curiosity and the desire to understand the unknown. Thus, the light of the first galaxies not only lights our way but also invites us to keep exploring. It reminds us that although we may see the universe more clearly today, there is still much more to discover in the vastness of the cosmos. With each new star that forms and each galaxy that lights up, the universe offers us new questions and mysteries that continue to challenge our understanding. The story of light and darkness remains a fascinating chapter in the narrative of the cosmos, and it is far from over. The light of the first galaxies emerged like a whisper in a universe that had remained silent for eons. But what does this moment really mean? And how did it change our understanding of the cosmos? To understand it, we must first imagine a universe that was once completely dark, where light did not exist. As the universe expanded and cooled, the first structures that would give rise to galaxies began to form. But how did this transformation occur? The first galaxies started to form about 1 billion years after the Big Bang. During this period, space was filled with gas and dust, and gravity began to play its fundamental role. Imagine gravity as a magnet that attracts small particles. As they come together, they create dense clouds that eventually become stars. But what happens when these stars are born? When a star ignites, it becomes a kind of beacon in the darkness. Nuclear fusion in its core releases enormous amounts of energy, resulting in the creation of light. This process not only illuminates space, but also contributes to the formation of new elements. Stars are true factories of elements that are later dispersed throughout the universe when they reach the end of their life. But why is the light emitted by these first stars so important? The light from these first galaxies not only brought clarity to a previously dark universe, but also marked the beginning of a new era in cosmic evolution. A lit universe is a universe that can be explored and understood. Light allows astronomers to study the composition, temperature, and movement of these distant galaxies. Without the light from these stars, our knowledge of the universe would be infinitely limited. But how do we know that these first galaxies really existed? Scientists have developed sophisticated techniques to observe the light that has traveled through time and space. They use powerful telescopes that can capture light that has been traveling for billions of years. In fact, when we look up at the night sky and see stars, we are seeing light that has traveled from long ago. Even before our own Earth existed, this means that every twinkle in the sky is a reminder of the universe's past. But what about the oldest and most distant galaxies? Observations have revealed that the first galaxies were different from those we see today. They were smaller, dimmer, and primarily composed of hydrogen and helium. Their formation was a chaotic process where gravity and radiation played a crucial role. In this cosmic dance, the light from the first stars helped ionize the surrounding gas, a process that drove the reionization of the universe. But why is this phenomenon relevant? Reionization was a key event that allowed light to begin traveling freely through the universe. Before this process, the universe was filled with free electrons that scattered light, creating an opaque environment. However, as stars began to shine, their radiation ionized the gas and allowed light to propagate. This change was fundamental for the universe to become transparent, opening the door to the formation of more complex structures. But how does this relate to everything we know today? The light from the first galaxies not only illuminated the cosmos, but also laid the foundations for the formation of the galaxies we see today. As the universe continued to expand and evolve, galaxies began to cluster into groups, forming a complex network of cosmic structures. This network is like a vast fabric that connects everything that exists in the universe. Without the light from the first stars, this fabric would not have had the strength necessary to develop. Now you might ask, what implications does this have for us here on Earth? The light from those first galaxies offers us a window into the past, allowing us to explore not only the history of the universe but also our place within it. Every time we observe the sky, we are looking back in time, reliving the story of how our cosmic home was formed. But what will happen in the future? As telescopes continue to advance, we are likely to discover more about these first galaxies and their light. Each new discovery brings us one step closer to understanding the mysteries of the universe. The light from the first galaxies not only teaches us about the past, but also invites us to ask questions about our future in the cosmos. So the next time you look at the starry sky, remember that each star and each galaxy is a testament to an incredible journey that began billions of years ago. The light from the first galaxies is more than just an astronomical phenomenon. It is an essential part of our cosmic history. It connects us all and reminds us that the universe is a place full of wonders and mysteries waiting to be discovered. The quest for light and knowledge is a journey we are just beginning, and every question that arises is an invitation to delve deeper into the understanding of the vast cosmos we inhabit. The reionization of the universe is a fascinating chapter in cosmic history, one that allows us to glimpse how darkness was slowly replaced by light. What happened in that vast stage where everything seemed still and silent? Initially, the universe was shrouded in deep darkness, a time when stars had yet to be born. However, this darkness was not eternal. As the first stars began to form, an astonishing phenomenon took place. Reionization. What is reionization and why is it so relevant? To understand it, let's think of a dark room. Imagine that suddenly someone turns on a lamp. At first, the light may not fully illuminate the space. But gradually, as more lights are turned on, the room becomes bright and warm. Reionization is like turning on those lights in a universe that had been in shadow for millions of years. During this period, the first stars and galaxies began to emit light, and that light had a profound effect on the surrounding environment. When the first stars shone, they released enormous amounts of energy in the form of radiation. This radiation had a direct impact on the hydrogen gas that filled the universe. But what happened to that gas? In its original state, hydrogen was made up of electrons and protons that were bound together in a neutral state. However, the energy from the stars was so intense that it began to break apart those atoms, separating electrons from protons. This process is what we call reionization. The question that arises is, when did this process occur? Scientists estimate that reionization began approximately 600 million years after the Big Bang. Imagine a clock that has been silent, marking the hours in darkness. Suddenly it begins to sound, marking the start of a new time. This was the moment when light began to dominate the universe, transforming darkness into cosmic splendor. To better visualize the magnitude of reionization, let's think of an ocean. If the early universe was an ocean of hydrogen, the light from the first stars acted like intense heat that began to evaporate the water, dispersing the vapor into the air. As more stars formed, more vapor was released, creating an environment where light could travel freely. This transformation was crucial as it allowed light to begin crossing vast distances in space. But what consequences did reionization have on the structure of the universe? Reionization not only released light, but also allowed for the formation of more complex structures. With the ionized gas, gravity began to play a fundamental role, attracting matter and forming the first galaxies. Each star shining in the cosmos was like a spark igniting the fuse for the creation of new galaxies, which in turn would merge to form larger clusters. Some scientists have compared reionization to an orchestra. Imagine each star as an instrument that, when played, emits a beautiful melody. As more instruments join in, the music becomes richer and more complex. Thus, the stars came together in countless combinations, creating a universe filled with light and diversity. Isn't it amazing to think that the music of the cosmos begins with the vibration of those first stars? Reionization also had an effect on the conditions of the universe. By removing neutral hydrogen, it allowed light to travel unobstructed. Before this process, the universe was opaque, like a dense fog that prevented seeing beyond. With reionization, that fog dissipated and galaxies began to become visible. But how do we know this happened? The evidence comes from modern observations of distant galaxies and the cosmic microwave background radiation, which tells us of a transformed universe. As scientists study the phenomenon of reionization, an intriguing question arises. What role did the first stars play in the formation of the elements that make up the matter we know today? Stars, in their life cycle, create heavier elements through nuclear fusion processes. These elements were released into space when stars exhausted their fuel and exploded as supernovae, seeding the universe with new matter. Reionization was not just a cosmic event, it was a paradigm shift. It transformed a dark universe into a vibrant and dynamic landscape filled with stars and galaxies, laying the groundwork for the subsequent evolution of the cosmos. Without this period of reionization, we may never have had a universe like the one we know today, full of wonders and mysteries. The exploration of reionization also invites us to reflect on our place in the universe. What does this tell us about time and space? By understanding how light emerged from darkness, we connect with the history of the universe and ultimately with our own existence. Like the first stars, we too shine in our little corner of the cosmos, trying to understand the vast universe that surrounds us. Reionization, then, is not just a scientific event, it is a reminder that light can emerge even in the darkest moments. In a universe full of uncertainty, there is always room for hope and discovery. So, the next time you look at the stars, remember that each one is a beacon from an ancient time, a witness to reionization and the beginning of a cosmos filled with life and possibilities. The formation of structures in the universe is a fascinating concept. How do we go from a homogeneous and hot cosmos to a vast space filled with galaxies, stars, and planets? The answer lies in a very mysterious and powerful process: the interaction between dark matter and gravity. To understand it better, let's think of a barn in the countryside. Imagine that on a sunny day, the wind gently blows, making the leaves slide back and forth. Suddenly, a strong wind sweeps everything in its path, forming whirlwinds in the air. This is how gravity acts on dark matter in the universe. Dark matter, although we cannot see it, plays a crucial role in the formation of structures. It behaves like a kind of scaffolding, an invisible skeleton that allows visible matter such as stars and planets to group together. But what exactly is dark matter? It is a type of matter that does not emit light or energy, making it completely undetectable by our instruments, but we know it exists because its gravity affects the things we can see. In the early universe, after the Big Bang, matter was distributed uniformly. However, small fluctuations in the density of matter began to occur. Imagine you are in a pool and you throw a stone. The waves generated on the surface of the water are similar to those fluctuations in the universe. As those small irregularities expanded, gravity began to do its work, attracting more and more matter towards them. The areas of higher density became gravitational traps, accumulating more matter around them. It's like having a magnet and starting to attract iron filings towards it. Over time, those concentrations of matter became large enough to form the first galaxies. But why is this important? These galaxies are the building blocks of our current universe, the foundation upon which all the structures we see today were built. The process of structure formation is not limited to galaxies. It also includes clusters of galaxies and filaments that stretch across the cosmos. These filaments resemble a gigantic cosmic spider web connecting galaxies and clusters in an almost magical network. But what about dark matter in all this? Its influence is fundamental. Without it, the structure of the universe would be completely different, and perhaps galaxies as we know them would not exist. As galaxies began to form and interact with each other, they also created environments conducive to life. Stars were born within these galaxies, and with them, the essential elements for life. But how does this relate to the universe we see today? The answer lies in the story of cosmic evolution. Every star that shines in the sky is a witness to that process of formation and transformation. Interactions between galaxies led to mergers and collisions, which in turn created new structures. Imagine two rivers meeting and mixing. In this way, galaxies came together, generating new stars and often destroying others in the process. This cycle of creation and destruction is what has shaped our universe over time. However, it was not all an easy path. The forces of gravity also caused some galaxies to move away from each other as if they were in a race. This phenomenon is part of what we know as the expansion of the universe. But what does this mean for us? It means that the universe is a dynamic and ever-changing place where structures are born, evolve, and eventually disappear. The study of structure formation is not only exciting from a scientific perspective, it also leads us to reflect on our place in the cosmos. Every time we look at the sky, we are observing a story that has unfolded over billions of years. The stars we see are beacons of a distant past, reminding us that we are part of a universe much larger than we can imagine. As astronomers continue to explore the cosmos, new questions arise. What else can we discover about dark matter and its role in structure formation? How will this affect our understanding of the universe in the future? Each answer generates new uncertainties and drives us to keep investigating. In summary, the formation of structures in the universe is a testament to the power of gravity and dark matter. From the small initial fluctuations to the creation of vast galaxies and clusters, every step in this process is crucial for understanding how we arrived at the universe we know today. Reflecting on this not only fuels our curiosity but also connects us to the very history of the cosmos, reminding us that we are part of something much larger than ourselves. So, the next time you look at the stars, remember that each one of them is a remnant of a cosmic journey that began billions of years ago. Have you ever felt that the history of the universe is written in a kind of echo, a whisper that reaches us from the most distant past? That is precisely the essence of the cosmic microwave background radiation, a remnant of the Big Bang that allows us to glimpse the initial moments of our cosmos. But what exactly is this radiation, and why is it so fundamental to understanding the history of the universe? Imagine a summer day when the sun shines brightly and everything feels warm. The cosmic microwave background radiation is like the echo of that light, but instead of being bright and warm, it is a cold whisper that speaks to us of the universe's infancy. This radiation is a kind of noise that fills all of space, a thermal blanket that reminds us that the universe, in its early moments, was an extremely hot and dense place. In the beginning, just after the Big Bang, the universe was filled with energy and particles colliding with each other. But as it expanded, that energy began to cool, giving rise to a mixture of particles and radiation. Over time, this radiation shifted to longer wavelengths until it became the cosmic microwave background radiation we know today. Think of it as the sound of an orchestra at the end of a concert. Although the music has stopped, the vibrations still resonate in the air. This phenomenon was accidentally discovered in 1965 by two radio astronomers, Arno Penzias and Robert Wilson, who encountered a persistent noise in their equipment. Initially, they didn't know what it was, but soon realized they were capturing the imprint of the Big Bang. Isn't it fascinating to think that by listening to that noise, they were connecting with the very moment the universe began to exist? The cosmic microwave background radiation has a temperature of about 2.7 degrees Kelvin, which means it is incredibly cold. But what does this tell us about the universe? Temperature is a key. When the universe was young, it was filled with light and heat. As it expanded, that light stretched and cooled. Thus, the radiation we perceive today is like a window into a past where everything was chaotic and vibrant. Each photon of this radiation has traveled for billions of years to reach us. If you think about it, each flash of light we receive is a small traveler that has crossed vast space, bringing us a message of what the universe was like in its early moments. It's like receiving a letter from an ancestor who lived a long time ago. It tells us about their experiences, struggles, and environment. Scientists have used this radiation as a kind of map of the primitive universe. By analyzing its distribution and temperature, they have been able to gather information about how the universe was structured in its early days. Did you know that the small variations in this radiation are what have shaped the galaxies and structures we see today? It's as if every little bump in a road contributed to the formation of mountains and valleys in a landscape. But the cosmic microwave background radiation not only helps us understand the past, it also challenges our perceptions of time. In a universe where everything is in constant motion, this radiation is a reminder that time is not linear. Each photon is a point in history that remains present, waiting to be discovered. What other surprises does the universe hold in its depths? Moreover, the cosmic microwave background radiation has been crucial in validating the Big Bang theory. Through precise observations, it has been shown that this radiation has characteristics that perfectly match what would be expected from a universe that began in an extremely hot and dense state. It's as if we have a cosmic DNA test that supports our theories about the creation of the universe. With each advance in technology, we have been able to improve our measurements of this radiation, allowing us to see finer details and better understand the history of the cosmos. Each new discovery brings us a little closer to answering fundamental questions. Where do we come from? What are we? And most intriguingly, how will all this end? The cosmic microwave background radiation also invites us to reflect on our own existence. If the universe has a story to tell, what is ours? In a sense, we are all part of this cosmic narrative, a story that spans billions of years. Each of us carries within us the echo of those first moments, a deep connection to the cosmos. As science advances, we continue to unravel the secrets of the universe. Each new finding about the cosmic microwave background radiation is another piece of the puzzle that helps us understand our place in the vast fabric of the cosmos. Who knows what else we will discover in the future? Human curiosity is insatiable, and the universe, in its immensity, will always have more questions to answer. Finally, the cosmic microwave background radiation is not just a scientific curiosity, but a reminder that we are part of something much larger. In a vast, expanding universe, each of us is a small reflection of that primordial energy, a journey that began billions of years ago and continues to this day. Thus, when we look up at the sky, we are not only contemplating stars, but also the very history of the universe itself. The opaque era of the universe, that fascinating period when light was trapped in a sea of particles, offers us a unique window to understand how the cosmos formed as we know it today. What does this opaqueness really mean? To grasp it, let's think of a large concert. Imagine thousands of people packed into a stadium shouting and singing in unison. The excitement in the air is palpable, but if the lights were to go out completely, you would be left in total darkness. That was the universe in its youth, a place where light could not fragment and travel freely. During this time, the universe was an extremely hot and dense place, filled with electrons, protons, and photons interacting with each other. Photons, those particles of light that are so familiar to us today, were caught in a constant game of hide and seek. Every time they tried to move forward, they encountered an electron or a proton, forcing them to change direction. Can you imagine a path full of obstacles where every time you try to advance, something pushes you back? That was the universe in its early moments. A sea of particles that did not allow light to move freely. The opaqueness of the universe played a crucial role in its evolution. Without that dense cloud of particles, light would have been able to escape, and the history of the universe would be very different. But what caused things to change? The answer lies in expansion. As the universe expanded, it also cooled, allowing electrons to combine with protons to form atoms. This process, known as recombination, was the turning point in cosmic history. Light could finally escape, illuminating a universe that until that moment had been a dark and confusing place. Now, what is the significance of this moment? When light could finally travel freely, a world full of possibilities opened up. The formation of the first atoms, such as hydrogen and helium, laid the groundwork for the creation of stars and galaxies. In a sense, it was as if the universe had turned on a light in a dark room. Without that light, the first cosmic structures would not have been able to form, and we would likely be looking at a very different cosmos. Speaking of structures, the opaqueness of the universe also helps us understand how galaxies formed. During the opaque era, gravity began to play a fundamental role. Small fluctuations in the density of matter allowed it to clump together, eventually leading to the creation of the first stars. This is similar to how air bubbles in a soda group together to form a large bubble when the bottle is shaken. Without the opaque era, these small fluctuations might not have had the chance to grow. But what about the cosmic microwave background radiation? This phenomenon is like a fingerprint of the opaque era. When light could finally escape, it left a mark on the universe that we can still detect today. This radiation is an echo of the Big Bang, a tangible proof that there was once a moment when the universe was completely different. It's as if we are listening to a whisper from our cosmic past. However, the opaque era also raises interesting questions about the future of the universe. If our understanding of physics and cosmology has been largely shaped by this time, could there be more opaque eras in the future? The expansion of the universe and its eventual fate are subjects of debate. Perhaps in a distant future, light will be trapped again in a contracting cosmos. This idea leads us to question not only the past but also the future of the universe. It is fascinating to think that although we live in a universe full of light and color today, much of its history is marked by darkness. The opaque era reminds us that the cosmos is a place of contrasts, where light and darkness coexist in an eternal dance. This duality also invites us to reflect on our own existence and our place in the vast universe. Understanding this era is not only essential for astronomers and scientists, it also provides us with a broader perspective on our own history. By studying how the universe transitioned from opacity to light, we can see parallels in our own lives. Difficult and dark stages can be fundamental in paving the way for times of clarity and growth. Returning to the question of how this era influenced the current structure of the universe, it is vital to understand that every element, every star, and every galaxy we see in the sky today is a product of that dark period. The dark matter that holds galaxies together and the gas that fuels stars have their roots in that past. Without the opaque era, we might not be here discussing the history of the cosmos. Finally, the opaque era serves as a reminder that the quest for knowledge and understanding of the universe is an endless journey. Each discovery brings us a little closer to unveiling the secrets that still remain hidden. By reflecting on this era, we not only celebrate the light that finally arrived, but also the mystery and beauty of what is yet to be discovered. Thus, the opaque era is not just a chapter in the history of the universe, but a symbol of hope and curiosity in our journey into the unknown. The exploration of the universe has always been a journey filled with wonder and mystery. In our quest to understand the cosmos, we often find ourselves asking, what does our existence really mean in a vast universe that began with a burst of energy and matter? As we delve into the history of the universe, from its origin to its evolution, questions arise that lead us to reflect on our place in all of this. Is it possible that the study of the frozen time and the opaque era offers us clues about our own lives and the future of humanity? Let's imagine that each star we see in the sky is like a page from a book. Each one tells a story that has developed over billions of years. Like a book, the universe has a beginning, a development, and possibly an end. But what about the pages we have yet to read? The opaque era, for example, is a period when light could not travel freely. This lack of light not only darkened the universe, but also raises fundamental questions for us. If light is what allows us to see and understand the cosmos, what does it mean for our understanding of reality that there was a time when it was absent? When we consider the opaque era, it's like thinking about a moment in our lives when everything is on pause. During that time, the universe was full of possibilities, but also uncertainty. Matter and energy were in a primordial state, and although we could see nothing, everything was in the process of becoming something wonderful. This concept of frozen time invites us to reflect on our own lives. How many times have we found ourselves in situations where the future seems uncertain, yet we are in the midst of a transformation process? The transition from darkness to light is a fascinating journey. Isn't it interesting to think that just as the universe had to go through its own phase of darkness to give rise to the first stars and galaxies, we also face moments of difficulty that push us toward growth and enlightenment. Each star that formed was a beacon of hope, a symbol that even in darkness there is potential and energy waiting to be unleashed. Reionization, that stage when the universe began to shine again, reminds us that light not only illuminates but can also transform. When the first galaxies began to emit light, the universe ceased to be a gloomy place and became a canvas filled with colors and shapes. In our lives, light can represent understanding, connection, and love. What if we viewed our struggles as preparation for a new era of light in our own stories? Moreover, the study of the opaque era allows us to glimpse the relationship between science and philosophy. By questioning where we come from and where we are going, we not only delve into the realm of physics, but also touch on aspects of human existence. Questions about the universe and its evolution lead us to reflect on our own nature. Are we mere coincidences in a vast cosmos, or is there a purpose behind our existence? Dark matter, which plays a fundamental role in the formation of cosmic structures, also raises questions about what we cannot see. How many things in our lives are influencing us in ways we do not understand? Perhaps, like dark matter, there are invisible forces and connections that shape our experiences and decisions. Recognizing this can open our minds to new possibilities and perspectives. The first atoms, such as hydrogen and helium, are the fundamental building blocks of the universe. Without them, we could not have had stars, planets, or even life as we know it. This fact leads us to reflect on the small things in our lives. Often, it is the simplest moments and the most basic connections that build the foundation of our most meaningful experiences. What small particles in your life are forming the structure of your reality? The cosmic microwave background radiation, that faint light reaching us from all directions, is an echo of the Big Bang, the Big. Through it, we can hear the story of the universe. Similarly, our own stories are filled with echoes of past experiences that have shaped us. In this sense, each of us is a small fragment of the universe, laden with history and meaning. How can we use those echoes to better understand who we are and where we are going? Reflecting on the opaque era also invites us to consider the future. If the universe has gone through so many phases and transformations, what awaits us on the road ahead? The history of the cosmos is, in many ways, a metaphor for human life. It reminds us that everything is in constant change and that every ending can be a new beginning. Are we ready to embrace change and discover what the future holds for us? At the end of the day, the study of the universe offers us a unique perspective on what it means to be human. It forces us to confront our deepest questions and embrace uncertainty. Just as the universe evolved from darkness to light, we too can find our way toward understanding and connection. What lessons can we learn from the earliest stages of cosmic existence that help us navigate our own lives? The opaque era is not just a period in the history of the universe, but also an invitation to explore the unknown. In doing so, we can find a sense of wonder and openness that empowers us to face the future. The questions that arise from this study are ultimately the ones that define us as human beings. They remind us that although we are in a vast universe, each of us is an essential part of this incredible story. What does it really mean to understand the history of the universe? As we explore the origins of everything we know, from the stars that shine in the sky to the atoms that make up our very being, we face questions that transcend the simple act of knowing. How did the cosmos form? What mysteries does time hold frozen before the first photon? The search for answers to these questions not only connects us to our past, but also opens the door to a future full of possibilities. The history of the universe is like a vast book in which each chapter reveals secrets about our existence. As we read it, we realize that we are part of a cosmic narrative much larger than we could imagine. Isn't it amazing to think that at some point, everything that exists was compressed into a point so small it defied our understanding? That initial explosion, known as the Big Bang, not only marked the beginning of time, but also sowed the seeds of the matter and energy that shape our world. Through this narrative, we discover that the Planck era is a period where the laws of physics become blurry and where reality, as we know it, breaks down into primordial chaos. But what does this mean for us? It means that the universe is much more mysterious and astonishing than our perceptions can grasp. The questions that arise are endless. How was that matter and antimatter organized in the vast darkness? What drove matter to form the structures we now recognize as galaxies and stellar systems? Cosmic inflation offers us a clue. Imagine that the universe expanded in an instant like a balloon rapidly inflating. This phase not only laid the foundations for what would become our observable universe, but also reminds us of what transformation means. From a state of chaos to one of order, the cosmos teaches us that even from the greatest confusion, unimaginable beauties can emerge. As we delve into the era of radiation, it is fascinating to think about how a hot plasma cooled and allowed particles to begin to combine. This process, though complex, shows us that unity and collaboration are essential for creation, not only in the universe but also in our own lives. How many times have we seen good things arise from the collaboration and union of different elements? When the first hydrogen and helium atoms began to form, the spark of cosmic evolution was ignited. Each atom is like a small story within the grand narrative of the universe. But amid this creation, there were also periods of darkness. Moments when the cosmos found itself in silence. Cosmic darkness is not just an absence of light, but a reminder that even in moments of emptiness, there is potential waiting to be revealed. Primordial nucleosynthesis is a fascinating concept that shows us how, in the first minutes after the Big Bang, the light elements that constitute our universe were formed. Isn't it amazing to think that when we look around us, we are seeing the remnants of those formative moments? Every star, every planet, every living being is a testament to that elemental creation. When electrons and protons finally combined to form neutral atoms, a monumental change occurred. The era of recombination marked the end of opacity and the beginning of light. This event not only illuminated the universe, but also symbolizes the importance of transition and change in our own lives. Sometimes clarity comes after moments of confusion. The first stars that emerged after this moment of clarity were not only beacons in the darkness, but also forgers of the universe's chemistry. Have you ever wondered what role stars play in our existence? They not only light up the sky, but are factories of elements that ultimately make up everything we know. Then comes the crucial moment of the first photon. This instant, when the first particle of light was emitted, represents a milestone in the history of the cosmos. What does this first flash really mean? It means that the universe, a vast ocean of potential, finally began to show its splendor. Every flash of light we see today is an echo of that first photon, a direct connection to the beginning of everything. The era of opacity reminds us that sometimes to see the light, we must first pass through the darkness. This concept reflects in our own lives. Many times, we face difficult moments before reaching clarity and understanding. Life, like the universe, is full of cycles of light and darkness. As we explore the light of the first galaxies, we encounter the legacy of the opaque era. Every galaxy we observe in the sky is a reminder that even in the darkest moments, there is beauty and potential waiting to be discovered. This cosmic legacy invites us to reflect on our own existence and our place in the universe. Finally, the philosophical implications of this story are profound. What does it mean for us as human beings to understand that we are the result of such a vast and complex story? The quest for answers about the origin of the universe is not just a scientific question, but also an exploration of our own humanity. It invites us to question our purposes, our connection to the cosmos, and the role we play in this incredible story. In summary, understanding the history of the universe is embarking on a journey that takes us beyond the stars and connects us with the very essence of existence. Each discovery, each question brings us a little closer to understanding why we are here. In the end, the history of the universe is not just a tale about the past, but an invitation to imagine our future and to be part of the narrative that is still unfolding.